also just save the, yeah. So let's talk about some logistics. So the end of this term is like to December 13, right? So I guess maybe we'll just have the final project due on that day. I will just need a kind of like, I don't know. I will need presentation from you guys. I will need video presentation from you guys. It is similar to what I did like in screen capture, this kind of stuff where you just present, like record your presentation, and so but before that, like maybe I will give it optional, like whether you want to write a written report as well as a additional kind of like was extra credit, and so as I mentioned, like we won't have class next week, so we'll have midterm like 15, right? And I'm not going to give out any homework assignment this week as well. So, but instead I'm thinking like maybe I will ask you guys to send me just some kind of like an abstract of what you're planning to do for your project. Like maybe by 22nd, I will just set it up like, so it may be, I would say like 10% of the entire project. But okay, I gave basically what, whenever you hand, I mean, as long as you hand in your assignment, I'll give you 10% for that. Like I won't actually grade you, but I just want to push you to actually get started, because we don't really have much time there. Even by now it's less than, or it's more than a month or so, right? And so regarding project, it's open-ended. Like I encourage you to just work on the stuff you have been working on. You're graduate students already. You can try to look into the your own research problem and see if like you can either, because I for the later half, maybe less than half of this course, like maybe more like practical on like some of this influence technique and so on. You may use those to predict something and so on. Like it should be very much applicable like to many problems. Or like you may try to study like in terms of more theoretical, like entropy of something. Just have a problem, so you want to look at like amount of uncertainty there and here, that kind of stuff. So but anyway, like just give a thought on that, like, and hopefully you have something concrete idea, like you have an abstract by 22nd, like just hand me the abstract, and then like as again, like the final project will be due like 13th of, okay, I passed. Anyway, the final project will be,
The abstract also should be presented? No?
abstract, no, abstract you don't need to present the abstract, but
Just send
yeah, just send me just submit the abstract. And yeah, I will give more guideline in, yeah, on the website I mean later on, like I'm on Canvas as well, so you know what you are supposed to submit. So okay, this is the logistic. So I guess we'll just get into the main course here, like the materials. So we kind of like were like halfway actually on talking about PCA and principal component analysis. And okay, what we had last time, basically, let's see what we have here. It's a little bit messy. Yeah, we said like we have some random variable x, right? And so we have some random variable x here. What we try to do is like we have the coherence matrix of x, and also here we assume x is zero mean. Then as we diagonalize the coherence matrix, and let's say P is the eigenvector matrix, namely, basically, what does that mean? Do I have something earlier like? Yeah, okay. So basically, like your covariance matrix is diagonalized by P, so in the sense that you P transpose times this sigma times P will be equal to a diagonal matrix. So from that, then if you kind of transform X into some random variable P, Y, using the linear transform P, just multiply P transpose with X to get Y, then you kind of make it uncorrelated, and if we look at okay, and then when we have Y, we are saying that okay, what we're trying to do is we have the Y here, and let's say of course P is n by n. We start with X is n by 1, P is n by n, Y is also n by 1. Let's say we are trying to do some dimension reduction. That's what usually people use for PCA, right? We want to reduce the dimension. So then let's say we just keep the first m components of n components of Y, so where m is less than n basically. It can be much less than n. And then we look, so we only keeping the first m component, so therefore the rest we just set it to 0, right? So in the sense we have an approximate of Y, we call it Y hat here. Y hat is basically the first m components will be exactly equal to the y1 to ym in Y, and for the rest it's just equal to 0. And then we try to compare what's the error, mean square error of Y hat from Y. So that is this guy, and we say okay, this after some step we do a trace and so on and so forth. Eventually this will be just equal to the eigenvalues of the remaining eigenvectors from n plus 1 to n. And okay, I forgot to mention that also we're supposed to sort the eigenvalues.
Lambda.
Yeah, sort the lambda, so that the first m is in decreasing order, basically descending order. So the lambda 1 is bigger than lambda 2, bigger than equal to lambda 2, and so on and so forth. So then basically we show that this is equal to this mean square error is just equal to this lambda n plus 1 plus up to lambda n. So that suggests that this will be the optimum way to do dimension reduction, right? If we have Y here, we should always discard the one with the smallest eigenvalues. That's in this case will be the last n plus 1, sorry, the last n minus m eigenvalues. Yeah, n minus m. Yeah, this m, right? So that's here is n minus m.
Oh, yeah, that's right.
Yeah, we kind of, yeah, we should always discard the minimum, the minimum ones. So that's what we talk about
So
for Y. Yeah. Yes.
what is procedure for calculate the PCA? What is step?
Oh yeah. Actually, I haven't finished yet. So let me continue a little bit because this is talk about Y, right? How about X? Because what's going on is let's say we have a Y, we do some truncation or dimension reduction, or you get Y hat, right? But in practice you start with an X, right? Basically again Y is equal to some P transpose X, right? So of course P is unitary, and it's kind of actually I should say here I'm assuming basically X is real here. So P is a real matrix, or otherwise I should use Hermitian, honestly. So I don't want to make it complicated. So
Yeah, that is
Hermitian will be complex conjugate, and so I mean for unitary the definition is that way. You have a matrix is unitary if something like that, right?
Yeah.
The Hermitian of, but if your matrix is symmetric and real symmetric, is real, then real symmetric is Hermitian as well, but it's real, then basically you have something like that. That is Hermitian is just equal to transpose, right?
Yeah. That's
So
right.
I can just do transpose
Yeah.
instead.
Mm.
So yeah.
Yeah.
Okay, I just want to make a remark here because strictly speaking, I didn't mention this. I mentioned this is real, so this is that's fine. And of course of course we diagonalize the coherence matrix. The coherence matrix is real anyway, so I guess it's okay. So then I have this y hat here. I want to go back to some estimate of x as x hat, right? I can get the reverse just trying to multiply the inverse of P transpose. The inverse of P transpose is basically just P. So then the question is like, is that this is optimum as well? Like we say like the way we do this reduction is optimum, right? This truncation or dimension reduction, this is optimum, right? So but this step is optimum doesn't mean that like this is optimum as well, kind of, right? So we want to also look at like what's the mean square error for x minus x hat, right? The mean square of, maybe I'll write like that, x
Mean square error.
x minus x hat, or like x hat. The difference in
So py hat it mean that x hat. This one is x hat.
yes. Yes. This is x hat. Yeah. So and this will be equal to the mean square error is transpose x minus x hat, right? So because the column vector, this whole vector, so it's like that. Then again, I can use the trace trick here because this is just a scalar. I put a trace, doesn't change anything. Right, doesn't change anything. But then like trace, I can get into the expectation. So I have expectation trace of that.
When we should calculate x estimates.
Oh, well, we want to see like this step, like okay, the PCA is something like you have some initial, you have some high dimensional random variable with high dimensional data. Then you project to in another dimension,
Yeah.
project to another space.
Yeah.
Basically, in this space, like y now is not correlated, and then I do the dimension reduction, right, and get y hat here.
Yeah.
Now, but I want to get back something is like in the original space, right? So therefore, like I go back to x hat here, the original space. But what we are interested really, last time we mentioned like the difference between y and y hat, right? But what we are really interested should be like what's the difference between x and x hat, right? Because go through the entire procedure. So x hat definitely not the same as x, right? But we want to see like what's the error during this procedure. Yeah.
So x hat actually there is error in that.
Yes,
But
yes.
already reduction dimension.
Yes, because there's dimension reduction from y to y hat, so then you're yeah.
Yeah, that's right. Okay.
So
So you want to calculate minimum square error between x and x hat?
yes,
Oh,
yes. So then the mean square error between x and x hat is just this guy, and then I do a trace. This is a trace trick again, like because the scalar I can put a trace here. Then trace can get inside that, and then like the nice part about trace is that trace AB is equal to trace BA, right? We showed it last time, so therefore it's equal to expectation trace x minus x hat times x minus x hat transpose. Now I can pull the trace back outside again, like, so I have trace.
it's a bit above, I think.
No, it's not the same because you see the transpose is different, right?
No.
This one here is 1 by 1. And actually this guy is n by n, right? Yeah. Yeah, this is n by n. So this is actually the coherence matrix, right? This is exactly the coherence matrix, right? This is the definition of the coherence matrix, right?
Yeah.
And so Therefore, I know that then let's see. Then also we know what we know.
Why
Yes,
in there is no trace?
yes.
In here is the estimate, and in
Oh,
here
yes,
why
yes,
there
yes.
is trace?
Because this is a 1 by 1 matrix. This is a scalar, right?
Yeah.
So what's the definition of trace? Is just summing the diagonal, right?
Oh,
So
yeah.
therefore, if you trace a scalar, for example, trace so 2 is just equal to 2, right?
Yeah.
Because 2 is also a matrix, right? It's a 1 by 1 matrix.
Mm.
So it's a dummy thing. Like I can put a trace here, it doesn't change anything.
Also, it means that this one is same with this one.
Yes,
And even this is 1 by 1.
because it's a 1 by 1 basically, right? It's
Oh.
it's 1 by 1. Therefore, I can put a trace here.
Okay.
Yeah.
That's right. Okay. So why you use trace in there? Why you want?
Yeah,
why
because
you trace there?
if I don't do this trick, I cannot change the order. This one here, right? In general, I cannot have like expectation this times this is equal to expectation. I mean, like I don't have like AB equal to BA, right? In general,
Oh.
yeah.
Yeah.
Because the matrix, I cannot just swap it.
Mm.
And actually, there's no way AB equal to BA, like because this is 1 by 1, this is n by n actually. Yeah, but using the yeah, this is kind of light trick here. So, but I know that what is x and x hat. Like x hat is p y hat, right? X is actually because y is equal to p transpose x. That means that like x is actually just equal to py. Yeah, because like p is unitary or orthogonal. P transpose p is just equal to identity.
Yes.
So inverse of p transpose is just equal to p. Yeah.
Because y is p transpose x. So that's you want to get x just.
Yeah, x equal to py.
Oh,
Yeah.
that's right.
Yes. So therefore, like let me substitute that one here. So so then I can substitute that. I get like trace expectation like py minus py hat. This is like py minus py hat transpose, something like that, right? My p can pull it out, so it's like something like expectation py minus y hat. And similarly, this like is like py minus y hat transpose, right? So therefore, it's equal to trace expectation py minus y hat trace p something like there's a p transpose here. And again, like the nice thing about trace is that I can put it back again. So it's equal to expectation trace this guy p minus y hat trace transpose p transpose. And now because you have trace AB equal to trace BA, right? I can say this is A, for example, this is A, this is B. So yeah, I trace AB is equal to trace BA. So therefore I can put it here, then I P transpose P, y minus y hat transpose. And I have traced this one expectation.
So why? Oh yeah, that's.
Then this guy cancel. That's a nice thing. So that is the same thing as the expression we had last time. It's just a expectation trace of this guy, and we know that is again it's just lambda m plus 1 plus up to lambda n. Yeah, and again this is therefore you can see the error is actually the same. Like whether the space is here, in the y space, or like in the x space, the mean square error is the same. Actually, by the way, just a remark here. This is I forgot. This is exactly the same as like you in Fourier transform. The power in Fourier transform is the same as the power in the spatial domain, in the time domain. Yeah. So this is like exactly the same thing. I forgot the name of that.
Transform that.
Yeah. I think that's I forgot the name of that theory. I just forgot. But this is a very general. Like if you have a orthogonal, because that's another thing. Like nice thing. If you think of like all this transform, what it's doing, it's really just rotating the axis. When you have a unitary transform multiplied by something here, what you did is really just rotating the axis. For example, like original your signal, you have a distribution and your scatter, the data is like this, whatever. Oh, maybe I have random variables and my sample some data got data like this. And then like when I have a transform, this kind of like orthogonal transform, that basically I have like some P is orthogonal or like unitary, and I multiply that by this P here. So what it did is essentially just do a rotation of the axis. So I have a rotating the axis into, let's say, this. And data is the same here.
Why you rotating why?
What you mean that why it is a rotation, or like why you want to rotate it?
Why you this rotation? I mean, why when we multiply by P, it will be rotation.
Why is a rotation? Oh, that's kind of a long story. Okay, that would be long because that's okay. Actually, that's how can I? So, it only true when this is satisfied.
Yeah.
When this is a unitary transform, so then this kind of linear transform applied to that would be a rotation. Or rotation. It's a general. I shouldn't say just rotation because it can also be a reflection. For example, you can access yeah.
How much rotation? How many degrees will rotate that? How many degrees from before? 90 degrees?
No, this can be arbitrary. It depends on because this condition you see that this is pretty general, right?
Yes, that's it.
For example, I'll give you an example of this. Unitary transform. So for example, you have rotation transform. It's like that, right? Cosine. Let's see, cosine theta, sine theta, sine theta, cosine theta. Let's say. Is that? And this thing is one of those unitary transform.
That is unitary.
Yeah, and you can verify that, right?
Yeah.
And if you do this called A, then you see like A transpose is equal to identity.
Yes, that's right.
Yes.
I like.
And this is an example. I mean, like in general, when this is satisfied, you have something very similar to that. But it's like, of course, like you can be more than like 2 dimensions. You can very high dimensions. But what happened is like, actually, what happened is more like it's kind of like this. What we discussed here is like a semi proof of why it happened. Because if you look at that, like, if you look at the distance between any 2 points, here, like, we are basically like compute the distance of any 2 points, right? Of course, what I want to say, this one we are computing the mean square error, but the same step you can use it to compute the distance between any 2 points in the space, right? And if you go through the same proof here, the distance at any 2 points in the space in the original space after this transform will be the same as like after the transform, right? So it means that this transform itself will keep the distance of any 2 points in space does not change. And then intuitively, this is not a rigorous proof. What kind of transform can do that? Only very few transform, rotation, reflection, that kind of mixture of them. Like only this kind of transform will allow you to keep the distance between 2 points to be the same. Yeah, and
the perspective will be different. That is the distance is the same, but because we see the need
yes,
for this
yes, that's why this.
distance.
That's.
Oh, I see that.
Yeah. FFT etc. I mean, Fourier transform is one of those transforms, and that's why you can see that Fourier transform, the power in the original domain is the same as the power from the frequency domain, right? Because what is power? Power is basically just the distance between the zero signal, right, from the origin, right?
Yeah.
So it means the distance from the origin is the same after the whatever your rotation and so on.
Mm.
Yeah.
So we want to rotate so something that will be reduce dimension then.
We
We want to rotate some with some angle,
yes.
and then we can reduce some dimension.
Yes, actually, this exactly manifests in this example here.
Mm.
Let's say if I have this signal, it's like this, right?
Yeah,
The signal like this, right? What's the best
the best.
axis to represent this signal? It would be like this axis, right?
Yeah, that's right.
Right. So, what PCA does, I mean, this unitary transform does is when you're trying to diagonalize your coherence matrix, it's basically rotate to the axis that like those components will be kind of like each component will be independent, not independent, uncorrelated to each other. So it will be rotated to this axis. And once you rotate it to this axis, then you can just go for the axis with highest variance, right? And this will be this one, right? So you want to keep this one and probably this discard this one.
Yeah. Oh yeah, that's right.
And then like after you did that, like then therefore like this is basically you have your transform, like P transpose X. This is like then you have your Y hat will be something like after your projection, what you have is like will be like all lie on the axis, right?
Yeah.
Because like the Y, this component you just disregarded, it become like this, and then you go through the P Y again to get back X hat, like Py hat again. Then will be like just getting signal now. It's like the original domain, but like it's like following a line like this. So that is what PCA actually did.
So only one line then after.
Yeah, because
line?
in this like 2 dimension, we just reduce to 1 dimension, it will become a line, right? Because if I discard like this this dimension here, this this component here, then everything like will just projected on this line, right?
Line on that.
So therefore, you will just get back the data will be just on this line here.
Yeah, that's right. So what the benefit then? We can see
You reduce the
clearly-
dimension now.
We can see clearly the difference between before, because before there are a lot of scatter, and now more precise. Yes, that's right.
Mm.
Because in here we have a lot of scattering, then the result now more sharp. That's the benefit.
The benefit is like something like you have a simpler representation, right? Or the less you need less number of bits to store your representation, right?
Yeah.
Here you will need 2 numbers to represent, right, originally.
Yeah,
Here you
that's
just
true.
need 1 number, right?
Yes, that's right.
Well, one thing like okay, of course there are several applications. One you can argue is like compression, where you basically compress the original signal from maybe you have like 100 components. Now you only compress to 10 components, right? Let's say if your M is like 10, like N is 100.
Yeah, that's right.
Or you can say like you reduce the number of features. Typically, what people did like before like doing neural network in the past is like this is the first step for classifier, right? Maybe you have a SVM afterward, support vector machine. Originally, like maybe the dimension is too high. You want to reduce the dimension or number of features there. So and then afterward, you put this feature into the whatever classifiers to further classify your data.
Yeah, that's right. And then you can easily to find
Yes.
the pattern.
Yes. And
Classify something. What the example for classifying?
for example, you can have like okay the maybe classic one. Maybe you can have a face recognition, right? I have face here. Of course, I want to align the face. Maybe let's say I already aligned the face. This is low. Say, I hear someone. Okay, it's a very wide face recognition. But let's say I kind of okay. I create a bounding box here. Okay, I already align everything, and I have different face like for different people here. So a simple solution will be like I dump all this data into a vector. So maybe this is like 100 by 100 pixels, right? Then originally I have like 10,000 dimensions.
Yes,
It's pretty high. now I can do a PCA. I reduce to maybe like 100 dimension or like 50 dimensions, and then I can do a classifier, any kind of classifier. You can use SVM or maybe just Lewis label, right? Maybe you just have like the same. You have like 10 people here, and when you reduce to 50 dimension, then you have the 50 dimensional space. Then you have like 10 points here representing in this space like 10 people. Then when you have a new photos coming in trying to recognize, then you just see like which one is closest, right? So, but instead you're handling in the 10,000 dimension. Now you're only handling in the 50 dimension. It's much easier. Yeah, and it's not just much easier because when you are running in 10,000 dimensions, you need to, because all this is like stochastic, right? So it's not like you have one data point will be sufficient. Because there will be error and so on, right? There will be fluctuation, right? So when you live in a higher dimensional space, the fluctuations will be, what should I say? The error will be more sensitive to this kind of fluctuation. Yeah, and when you are in a lower dimensional space, like there will be like more tolerance, like that you do not have a good estimate of the coherence matrix.
And then after that, we can find something like last time in the computer vision, we find what I forget the basis for pattern for all of that.
Oh, you mean like, oh yeah, that one actually, that is the eigenphase. I guess you can. So eigenphase is basically, okay, you do the PCA, then you have the eigenvector. So you look at the phase, because then you have the vectors, I should say, like you have the vector here, 100 dimension, maybe you go down. I don't need to really fall down to 50 dimension, but I do the rotation now, so from X to Y, right, in a different space. Now I go for the highest eigenvalues first, and look at the corresponding eigenvectors. And the eigenvectors will also be like 100 dimension, right? Oh, sorry, 10,000 dimensions. But that can be arranged back to a 100 by 100 image, right? And the 100 by 100 image will be just something look like a face.
Yeah.
That would be like the most significant components.
Yeah.
And then you can go like look at the next most significant component and so on and so forth. And yeah, that's the eigenphase.
Most significant component. We find most significant.
Yeah.
So that is the same with the PCA.
Yeah, it's exactly the same. It's just an application of PCA. Yeah.
We already done the application, but we don't know the theory.
Yeah.
Okay.
So and final remark about like PCA is that in practice, typically we say like we compute X segment. Oh, okay. Typically, what we have is we have data first, right? Let's say we have data. We say X is a random variables, but in practice we have data coming in instead, right? So let's say I have X bar is a sample of X. So not X bar, like this script X is like some sample of X. Let's say this is like I have like, let's say M sample of X. Maybe this way better this way. Like M sample of X. Like this. So and this is like n dimensions. And typically like your samples typically will be less than the number of your dimension. It's less than the dimension actually. Sometimes it can be even way less. If you're talking about a very high dimensional data, for example, you have this data as I said, like for example here maybe it's an image, maybe it's not 100 by 100, but maybe like 1,000 by 1,000, right? It's a reasonable resolution. Then it's already like what, a million, right? This will be a million, right?
Million, sorry?
A million, or like a million. The dimension here n would be a million, right? But you may not have a million pictures, like for whatever. Maybe you have like 50 or like 100 or something. Then what you try to do, like we try to estimate the coherence matrix, right? strictly speaking, like how do we do that? If we have this, it will be
And so what this is the our data.
yeah. This is our data.
This is and this is one data.
Yes.
This is one data.
Oh,
and
yes.
we have m.
M of
data.
them. Yes.
Why you should have m of them?
Or you can have more. I just arbitrarily say a number.
I mean that is photo. That is a picture.
It can be like
And then and it is and it should be a times a by a. It means that because we have picture is
if it's a picture, yes. If it's a picture, it will be A by A. Yeah.
Okay, a by a is n equal to n.
Yeah.
Oh.
If it's a picture, let's say like if 1,000 by 1,000 will be a million.
So why we should have a lot of data?
Yeah, because you need to estimate the coherence matrix, right? You want to estimate sigma. What is sigma? Sigma should be like you need to compare what?
Oh yeah, that's variance and then correlation.
Yeah. So because let's say what's the reasonable sigma? So assuming again, I assume it's still mean here. Then let's also write this matrix as like x1, maybe just x1, x2, xm. So let's say this is row vector now. This is row vector.
So that is something like maybe like a movie. This is because this picture. So it's been like movie.
It doesn't necessary because for example,
There is
I
correlation.
use the eigenface example again, right? You may have your 100 faces like in your database, maybe like 200 or like 300 or 500,
And then
but you have so
the face is can be different. My face.
yeah, it can be different, like different faces. Yeah,
Okay, I see.
that would be your data, right? And
Okay. Okay, I understand.
now let's say so what is the coherence matrix supposed to be estimated, right? It should be something like xi. Okay, I need to be careful now. This is row vector. xi transpose over m, right? Is that correct? Let's see. Oh, sorry. I should write like this. Wait. I make. Let me just.
We should have variance in the diagonal and then correlation in others. That's right. The matrix of sigma.
You mean the sigma? Yeah.
Yeah, sigma is a variance in diagonal, and then
Yes.
other is correlation.
Yes, but remember, we need to estimate those variance first, right?
Yeah, that's
We
right.
don't know that. Like we only have again. I repeat again. Like what we have in practice typically is not we don't have the actual distribution, but we just have the data, right?
Yeah.
So we have the data. It's like so many data points. I say m data point here.
That's right.
So now we need to estimate back this coherence, right?
Yeah, that's right.
And the coherence one, I'm claiming it should be just like this. This is a row vector. Okay, I need to be. So let's see if it makes sense. Does it make sense to you?
You should have two I and J maybe because we
No.
different.
No. Be careful. Like this is a vector itself. Like this is a vector. This is a vector of the sample.
But that
so-
will be same always. We don't have x2, x1, xm.
Let me write this way. Maybe it looks clearer. So I have a sample like this. This is a transpose, and this sample like this. This is my x1 transpose x1, and plus like x2 transpose x2, and so forth up to xm transpose xm. So now let's look at just the one of the element. Let's say look at the ij element. So what is the ij element? Why is it moving like this? So what's the ij element of this guy? The ij element. So the ij element will be like x1 maybe I write like this, x1i times x1j, right?
Mm-hmm. That's right.
Plus x2i, x2j,
Mm-hmm.
so on, right?
Mm-hmm.
xmi, xmj, right?
Si. That is I is always same.
Wait, x1i, x1j, okay, I shouldn't write equal here, but like this,
This is x1 and x2 same. X1 and x2. No, this is x2
yeah, this is x2, yeah.
and this is x1j. What is x1j here?
Oh, okay, let me repeat again. Let's say I'm basically claiming that this is an estimate of the coherence matrix here.
Yes, that's right.
I'm arguing why it's so because I look at the ij element of this matrix here.
Mm-hmm.
The ij element of this matrix here is this guy, right? It will be like the x1, the ith component.
Mm-hmm.
I write x1i multiply the j component of x1 again. So I have x1i times x1j, right? And this one will be x2i times x2j, and so on, right?
I mean, where is the x1j here?
Oh, here, look at this one. This corresponds to this one. x1j will be like the j so x1, this is a row vector, is equal to x1, 1, x1, 2,
Mm-hmm.
up to x1n.
Mm-hmm.
It's basically a vector like this.
Mm-hmm.
So x1j will be like the jth component here.
The j component. What is the j component on there? From there? What is the j component?
The j component here
Yeah, from there. Yeah.
will be just a j component of this. So this j will be between 1 and n. Some j, right?
Oh, does mean that this one is j.
Yes.
Okay. So actually, this is 1 comma j.
Yes.
Comma.
Yes, it's comma. Yeah, 1 comma j. Yeah, 1 comma j. Let me write it better.
That's one x1 x1 x1
x2 comma j, x2 comma x2 comma i,
this
x2
is
comma j.
represent this one
Yes.
x.
The
This is,
the ij component. Okay, look at this as a matrix,
mm,
and the ij component of this matrix will be just x2i multiplied by x2j, right?
x2i I multiply the x2 in here si something like that, something like that.
Yeah.
Oh, so this is j go here.
Yeah.
So this is x1 x1 j1 j2 j3 j4 until then until finish. That's right. If you like yeah, if like that is
This is I. Yeah. This I go down this I.
yeah, that's I.
The ith component.
Yes, that's right.
And basically this matrix you have like yeah. Look at the ij component will be just this, right?
Yeah, that's right.
Yeah.
Yeah, so that will be like that. Yeah, I is go down and j horizontally.
Yeah.
Okay.
And you look at like this term is basically look at the estimate of correlation between ith and j term, right?
Mm.
So this is actually is an approximation of expectation xi xj, right?
Yeah.
Xi times multiplied by xj, right? And this is exactly what we expected for a covariance matrix, right?
Mm.
When it's zero mean.
Mm.
Yeah. So therefore, like okay, this is the covariance matrix, and this I can write it as a matrix form. If my vector is written in this way, and you can verify that this is actually just equal to m. Let's see. X. Let's see. X transpose.
Oh, that is for only one dimension.
What?
This is for only one dimension. And then you want to write in many dimensions, multivariate.
Oh no.
No?
This one I'm arguing this one is correct.
Mm-hmm.
Do you agree with that?
Yeah, that is variance, covariance.
Yeah, this is like the estimate of covariance, right?
Okay.
Now I'm just saying that okay, because I also have like my x, I have like x1 up to xm. I can pack it as a matrix script x here. X1 here is all row vectors here. So then this actually I can write it as, okay, maybe I can just maybe do one more step. It would be like x1 transpose, x2 transpose, xm transpose times x1 xm, right?
There is no correlation in between them, Dr. Chen. In here, in this formula, there is no correlation.
Oh, okay.
between
I'm
X1,
okay. I'm
X2.
explain. I explained that in here. I thought you got this. I explained that in here. This is equal to this.
Yes, that's right.
I'm saying like for this one, the sum here. If you look at the ij term, it's equal to this. You agree with that, right? The
Yeah.
ij term is equal to this. And what is this? This is just an estimate of This is just an average of like xi times xj, right?
Yeah, that's right.
And the average of xi times xj is just an estimate of like this way expectation xi xj, and this is exactly the ij element of like sigma ij, right?
Oh, okay.
Yeah.
Yeah. So that is the correlation in between.
Yeah.
Under vector.
Yes.
Oh, okay, got it. Yeah, that's right. Okay.
Okay. So yes. So you, if you agree with this one, then this I can write it as this way.
Why?
Oh, okay. This you just have a kind of like matrix multiplication, right?
Oh, yeah.
This is
right.
how you do a matrix multiplication, right?
Yeah, that's
And but like if you look at this, what is this guy? This is just equal to x, right?
Yeah.
And this actually is just equal to x transpose.
Yeah. That's right.
So therefore, I can also write this as like 1 over m x transpose x.
Yeah, that's right.
So what I mean is like, so instead, like in practice, okay, it's not really in practice yet. So instead of like you trying to estimate the covariance matrix, diagonalize the covariance matrix, it's the same as I diagonalize essentially x transpose x, right? You basically want to, if I ignore this 1 over m is not important. I'm trying to diagonalize this into, as I mentioned, equal to have some p transpose p equal to some diagonal matrix, right? Something like that. But the problem is that, as I mentioned, your n here can quite a bit bigger than m in practice.
Oh, yeah.
So therefore, if you compute this matrix, like this is an n by n matrix, and you will have this matrix is like pretty much, it will be a pretty bad estimate. You have like lots of zeros here, and more importantly, like this is an estimate of covariance matrix, and covariance matrix is supposed to be positive definite. So if you remember, like we mentioned earlier, last time, so we showed that covariance matrix is supposed to be positive definite, right? But if you use this estimate, like often it won't be even positive definite.
Why
Yeah.
this will be a lot of zero if m less than n?
M less than n because because the rank is, okay, what is the rank of this guy? Rank of this matrix. So I have, let's go to here, let's say sigma, I can estimate as I will just write equal to x. I will ignore the m here, like I ignore 1 over m here. So I look at the rank of this guy, rank of a matrix, rank of the matrix, and look at the rank of here. And you know that the rank of like matrix A times AB will be kind of less than the minimum of rank of A and rank of B, right? So therefore, like this, both of matrices n by n, right? So therefore, like the rank of this guy has to be less than m,
Less than y, because
because it's an n by n matrix. The rank cannot be larger than the
so the minimum is
minimum. Yeah, the minimum is m because yeah.
Oh yeah, okay.
Yeah. So therefore, like the rank of this guy, if you estimate this way, the rank of this guy will be less than m.
Yeah.
But if m is like much less than n, so I should say there will be losses. But do you expect that, right? If you have a matrix, the rank is like is much lower than the size of the matrix, then you expect like it will be. It doesn't necessarily be a loss of zeros, but what I want to say, like it would be. I don't know how to say, but numerically it won't be very stable. First of all, like it would be very close to, okay, for whenever you have a zero, I sounds like kind of like trying to teach linear algebra now. So
Yeah, I know that. Yeah, n is will because less than r, therefore that will be 0.
yes,
Yeah.
but also like
Because the energy is will be less than n.
yeah, yeah, and also like when the zeros, the number of zeros basically correspond to number of like eigenvalues is equal to 0.
Yeah.
And so because you have low rank here, you have lots of eigenvalues of this matrix will be very close, will be basically 0. And but because it's 0, you have a it's hard to say. I guess I didn't have a very good kind of background of like numerical analysis, but this basically will
The solution is a lot of 0.
the eigenvalues will be 0, and like some of them will be like negative actually.
Yeah, that's right.
So when you have like eigenvalues are negative, basically you have a not positive definite matrix, right?
If we eliminate that matrix, that will be a lot of 0. Eliminate, there is some operation to eliminate matrix. That will be a lot of 0. That's right. Yeah.
Actually, I didn't get what you talk about.
When in the algebra linear, I found that if the rank of this m is bigger than m, so the solution will be a lot of 0 because that will be eliminated. Yeah, something like that.
Yeah, I guess I should take it back saying that the matrix itself with lots of zeros, but instead I want to say the eigenvalues of this matrix will have lots of zeros. I mean, lots of the eigenvalues will be 0. That's definitely correct. And numerically would be quite unstable because yeah, I cannot give a very good argument for that, I'm thinking. Of course, for one thing, like if you remember, like I don't know how to. I guess I won't try to explain because I guess should okay, I'm not prepared for explaining this part. So,
Okay.
but I like this is bad. Like my numerical analysis is not good enough to explain this. But you can try it. I mean, like if you try to just have like some matrices like m less than n, and then compute. I mean, you have to say.
Just by one example matrix, this is maybe 5 and this is maybe just 3, so we can make some elimination.
Or even like you can 1mn, 1m 5 or 3.
Yeah.
So then you have a matrix inside that where, like for example, you have 1 0 0.
Yeah,
Like I maybe I have just one data point here, 1 0 0, let's say.
yeah, 1 0 0.
Then I multiply this as under is a 1 0 0. So I have like this estimate covariance matrix, a 1 0 0, something like that.
And another is 0 0 0 0.
This is kind of, yeah, this is like both 0. All the rest is 0 basically.
But that is 3 by 3.
Yeah, that's 3 by 3. I have like
We should 5 by 3, something like that, because we have n more than n. So
oh yeah, okay. If you want, I'm assuming n equal to 3, m equal to 1 in this case. Just a very simple example here.
Um,
Yeah, so I have 3 by 3 here.
mm,
Yeah. Here, okay, I didn't illustrate how bad this is. So if you try to um, um,
a lot of zero.
there's a lot of zeros, and also like the thing is like not just a lot. Eh, you okay. What is the better way to it? Okay. Hmm. Okay, I give up on this part. You just have to trust my, or like you want to do, you can do some exercise yourself, like
Yeah.
and like this is a m by m, and then like you generate this x transpose x, and then try to diagonalize this matrix.
Yeah.
It won't give you some very stable solution. Basically, it's likely you will get something the okay, if you just look at it, oh okay, why don't I just try it here actually, honestly.
Yeah.
Let's see.
Yeah. Using MATLAB,
I have Octave for this. Let's see.
optic. Yeah.
So for example, let's say I have some x is some data like just like random and maybe n. Okay, I just say n is 100. Let's say m is equal to 5. Let's say.
Yeah, that's right.
Then I have like x is some data have just random, and I have like
And
size is like that.
M.
So
Yeah.
m.
Yeah, that's right. That's our data.
Yeah.
So we can
Oh, okay.
diagonalize.
Actually, I want to define the other way. Let's say let me put x is like that. So it's like each row is a data. So I have only
What's that?
I have 5 rows here. Each row is a data. So each data is a so, and then I find
A 5 column or row?
oh actually it doesn't matter, like because in what we have been discussing, like we just put the matrix this way. So I just want to be consistent.
Okay.
It doesn't matter actually.
Doesn't matter.
It doesn't matter.
So but in there, in this case, 5 in row.
5 rows, yeah,
Yeah.
5 rows, and like each row is 100.
Yeah.
So then I have x transpose times x. That gives me the estimate of the coherence matrix, right?
External.
Uh,
It's broken. Right?
I don't know why it's broken. Like x transpose times x.
External.
Yeah,
This transform.
yeah,
So S, that is S.
yeah. That's the s.
Um,
So now let's try to eigenvalue decomposition of s. Let's say.
with S.
Yeah,
That is eigenvalue. Eigen what?
yeah. That's eigenvalues.
Okay.
So you see, like it's supposingly the eigenvalue should be positive, but got lots of its negative, even the very small negatives. That's something that's not nice because I supposed to have a matrix positive definitely. I have something like very much.
That's a negative also.
Yeah.
So we should find the positive eigenvalue for all. So
Of course, I can still do this. I basically I can ignore the rest. I just take the biggest eigenvalues, eigenvectors.
the random maybe so don't have negative the random because random has negative.
No, but remember, okay, remember that it has nothing to do with that. We have the
Data.
whenever like you have
So our data is no problem. There is negative.
it doesn't matter
Doesn't
actually.
matter.
It doesn't
So
matter.
that is Gaussian also is good. I mean that you need zero means and then variance. That doesn't matter.
It doesn't matter. Like remember, like we show that like the coherence matrix has to be positive definite all the time, and we show it very easily. Like because the coherence matrix is like something like x hat, something like
But why in our experimental before previous there is negative lambda?
Yeah, that's exactly this numerical problem. Like you see, they are negative, but it's very small negative. It's 10 to the minus 15 or something like that.
Yeah. Okay, can we see that?
Yeah, 10 to minus. Okay,
Where is the
10 to minus 14, 10 to minus 15.
oh, yeah.
So it's numerical problem.
Yeah.
So take the cost numerical analysis. I mean, like this is numerical problem. It's like okay beyond the scope of my this course here, but just want to remind you that that can be the problem. Then okay, I'm kind of stretching too far, but the solution is basically we don't want to do this. Basically, we don't want to first compute sigma as where's my sigma? Yeah, we don't want to first compute this sigma as estimate of x transpose x and then do an eigenvalue decomposition.
Why?
A better okay. This is because it's numerically unstable.
Oh yeah.
So instead, you want to do SVD, the single value decomposition.
Instable because instable the macros. Sorry.
Yeah, you want to do single value decomposition instead.
You said because what's that unstable?
Or numerically unstable.
Numerical and unstable.
A numerical is
How to spell that?
numerically unstable.
Oh, okay. I understand.
Yeah.
Okay.
Yeah. So instead, the better way is to use SVD. So SVD is basically single value decomposition.
Yeah, I know that.
It's a way that you can decompose any matrix. It's not just square matrix. So it's assumed that any matrix M, you will have a SVD. It will be something you can write as U dV permission, something or if you have real matrix, then it will be UVD transpose, UDV transpose, where this guy is a orthogonal matrix if it's real.
And
Or
what is the M in there?
Oh, it's just any matrix, any matrix.
That is not our.
No, not our. It's just any matrix. It doesn't need to be square matrix, right? It doesn't need to be square. But for let's see. But if we're able to decompose like this, so assume SVD exists, then actually if you think of the SVD is I guess a good explanation SVD can be something okay, this is also a sketch, something like that. You can think of as when you have a matrix M, you can think of M as a transform. Let's say in a two-dimensional TD case, and basically I can have a transform that is going to rotate and scale your axis. So then this kind of transform can do it multiple steps. Where I can first let's see.
That's what do you say? It's something like PCA.
Yeah, kind of similar to PCA as well. So this will be or the rotation transform. This will be kind of PCA, similar to. So you rotate it. So to let's say to this way. Let's see. I didn't draw well here. Maybe it's better for me to.
But what is our data? N by N.
Well, actually, maybe okay. Let me skip this part. I mean, it doesn't matter. Just take it that I have a SVD. So because I think I was dragging too long.
N by N.
So
N by N there.
let's say this is our data is X here.
Oh, okay.
So let's say it's our X here. So if this we do SVD on this, let's say this is the X, they compose into this here. Then I look at X transpose X. It's X transpose X. I think it's X transpose X, right? yeah, X transpose X, it will be something like U D V, sorry, V, yeah, it's okay. U D V transpose U D V transpose, right?
Yeah.
But this guy is just equal to V D U transpose U D V transpose, right?
Yeah.
And these are unitary matrix, so this is equal to identity here.
Yeah.
So I have V D square V transpose.
V square. Yeah, that's right.
So this, as we said, this is our coherence matrix, right? This is sigma, right? So we are trying to diagonalize this matrix.
Yeah.
And when we try to diagonalize this matrix to find the eigenvector V, it's the principal component. It's the same as we apply SVD directly on the data X, because you look at this is the eigenvector V, right? In the
There
coherence
is
matrix.
D in there.
Yeah, there's a D square, but D square doesn't matter because this is still like the eigenvalues, right? Essentially, what it means is the eigenvalues of sigma is equal to the square singular value of X square, right?
Singular value of X squared.
Yeah, because these are the single value. Now the D is actually the single value matrix. And you see here when I diagonalize this sigma, I have like V D square V transpose, right? So then,
So
yeah.
it means that we should calculate first the D singular value. So we should calculate first this one D, and then after that we find this D square, and we find this D and V. That's right. The singular value first we calculate. We find first D in the singular value of X. We find the
Yes,
eigenvalues.
yeah.
Find
No,
eigenvalues.
no, it's the other way around. We want to bypass this actually. If we first compute, we first estimate sigma, and then I estimate the eigenvalues. That is exactly what we did earlier, right? Then we will find the D square.
Yeah.
But instead, like we don't need that. Like as you can see, if we just trying to find the single value of X, the square of the single values is actually the eigenvalues. And of course, like, we don't actually care that. Yeah, we care the single values, but of course, like the magnitude, we only care about the magnitude, right? We don't care exact the size because we just want to sort the eigenvalues, right? So the biggest eigenvalues is the same as the biggest single values anyway, because one is just the square of the other, right? And then and more, of course, we are more interested in the principal component. Basically, is the eigenvectors of sigma. But you can see the eigenvector of sigma is basically the left single vectors of X, right? So actually, instead of decomposing, first estimate sigma, and then decompose sigma using eigenvalue decomposition, we should directly decompose X using single value decomposition. And then V is basically our principal component. Yeah.
Yeah. So yeah, that's right.
So that's basically the entire PCA. So
V is what?
you mean the name?
Yeah, I mean that you already said that V is principal.
Principal component. Yeah. V is actually the principal component. Yeah.
So the first one, we should find the D. After that, we find the principal component, so we can find sigma then.
Actually, the whole procedure should be like that. Like you have the data X. Let's say you have data X is the data matrix.
Yeah.
If it's not zero in, make it zero mean first. Like you subtract the mean. Then afterward, you apply single value decomposition or this one. Then you get this UDV, right? And your D supposed to be sorted as well.
Yeah.
Supposed to be sorted. And you pick the largest single vectors, the vectors of V that have the largest single values.
Yeah.
And then for the
lambda.
yeah, Yeah, and for the rest, you just discuss. That is actually the lambda square root because there's a difference of square here, but it doesn't matter. The size, we only care about the size, right? We don't care about the exact value. So then, like, we have this, and then we can use V transport as the projection. Then you have whatever coming data you project to V using V, and then you just pick the one. So I mean, like, if you have incoming data X, then you will get V transpose X, right?
Yeah.
And then like you get this is basically Y, and then you have Y hat. Basically, is discard some of the components there. Then you have like V Y. You have like X hat is basically V Y hat, something like that going backward.
Yes.
Yeah. But of course, this is the entire procedure. Typically, what you did is that you have this here, going this step. Like after you find this, you sort all the eigenvectors, all the single vectors, and then you keep the components Y, and then you take the first M1 into a classifier. If it's a classification problem.
Yes. And then what the sigma then?
Sigma, we don't need sigma anymore.
We don't need sigma anymore.
We don't need sigma anymore. We directly use the our V is coming from here, right? V is directly coming from the data. We don't need to estimate sigma anymore. Sigma is supposed to be equal to this, 1 over m this, but we don't need that anymore. Actually, that's okay. I think that's a very another better explanation for what I talk about. In practice, also this is not very reasonable to compute sigma anyway, because, for example, this is like 10. The n is like 1 million. Then sigma itself will be a million by million, right? You have hard time even storing that. How can you do the eigenvalue decomposition for that?
Yeah, that's right.
You cannot compute like eigenvalue decomposition for that. So that's basically just intractable. So instead, like, it's always people will do that. Therefore, yeah,
Single SPD using SPD.
yeah,
So we process something like this for all this one or that, then we.
yes. And the V here is just coming from here. Yeah.
And then X will be already decreased dimension. Then we already have decreased dimension because
Yes. This basically in this Y basically, here is the Y space. In the Y space, you have a decreased dimension, right?
decreased dimension.
Actually, if you go back here, actually, you in the original space, then I'm not sure you can say it's a decreased dimension because you still have like n components there, and there's no COs there because when you project it back. But in Y space here, you basically have like n minus m components will be all COs, right? This will be all COs, and this will be like non-zero here because this is all discarded. Yeah.
So n minus m. So this one, what? How much?
That's m. That's
m. So
m minus m.
So what we got it? Only m by m. M by what? So
yeah, you can have like just m by 1 as y.
M by 1.
Because this you can ignore those.
Yeah, that's right. So that's no need to calculate sigma then. Okay. But why this one in here there is n x in here n by m?
X here is like n by 1, right?
N by 1?
Oh, okay. This x is different from this x. I'm saying like, okay, after you find the v here, let's say you have some new data coming in, is n by 1. Yeah.
So meanwhile we have n by m. Then why in here only n by 1? Why we use only n by 1?
This is like you can think of like this part is training, right? You can think of like this part is training, and this part is testing. This is an actual application, right? After you train the model here, you have a trained model, you know what's V now, you have a new data coming in, right? It doesn't need to be like M data at the same time, right? You can have one data coming in one at a time.
I see. Yeah, and then times by X, and we can find the Y, and then get this. How to get training in here then? V.
V, again, V will be here, right?
There.
So you start with the training data. The training is just packed into, like, as we mentioned here, M row and data point, like each data point has a row vector, let's say, and then you just do a SVD on X. Then you will get a V already immediately.
Oh,
Yeah.
yes. So the first thing it should be training first. This one we should done it.
Yeah,
and then
you
go
need to
there,
get V,
go
yeah.
up, go down. Okay.
So, okay, that's all I like to talk about. Please, I guess it's good time to stop now.
It should be done by using computer then. It should be using computer.
Oh yeah, it can only be,
calculation.
yeah.
Because law.
Yeah, if you do this SVD, like you should use computer too.
Yeah, interesting.
So I guess I will stop now, and then I will come back after 15 minutes or so. Then yeah, we talk about Gaussian again. Yeah.
So the important thing is